So the second part of lesson 7.6 is going to focus on starting with equations that are in logarithmic form and solving them from that form. Whereas the front of the sheet, we started in exponential form and had to solve from there. So we're going to need to keep those basic forms in mind. Again, like we have through the whole chapter. So here's our logarithmic form, and we need to keep in mind how that relates to our exponential form. And then we also need to remember that if we have this definition they gave us a couple of sections ago, if we have a base to an exponent and that's set equal to another base raised to a different exponent, uh, x and y we can say are equal. So we can actually set those two exponents together, set them equal to each other, and use that to solve the equation if the bases match. So we need to keep that definition in mind, as well as all those logarithmic properties that we've been working with. We'll need to use those as well. So looking at 28, we have it in logarithmic form. We have to remember that when our base is not recorded, like it is in number 28, there's nothing written down here in the base spot. That means that it's base 10. We just assume it to be base 10. So I'm going to write it out, the original problem out, but I'm going to go ahead and slide the 10 in there just so we can see it. So from here, we're in logarithmic form. We're going to go to exponential form, which would be 10 to the third equals x. And so we can see that x is going to be 1,000. All right, and that problem is that straightforward. So that's number 28 there. On 31, here is where this definition, we can use this definition up here, and I'll show you how. And it's sort of indirectly using that definition up there, but we've got the log base 7 over here on the left side, and we also have log base 7 on the other side. And so since both of those logarithms are sharing the same base, we can set 2x minus 1, 2 minus x equal to that 5x on the other side. All right, and then this becomes a very simple problem with x equaling 1/3 here. The other way to do 31 is to set it up as an exponent. So if I were going to go from log form here to exponential form, it would look like this. I would say I would have that base 7, and it's going to have an exponent of the log base 7 5x that's on the other side. Okay, and then that would be set equal to this 2 minus x. So maybe to make that a little bit clearer, if I come over here, let me switch colors. If I come over here under the original problem, you can see if I write the pattern out underneath, so we have log base b, here's my y, and that equals this x over here. So I'm getting that from my logarithmic form over here. I can take that base b, which is 7. My x is this log base 7 5x. That's going to become my new exponent, and then I set it equal to that 2 minus x. I'm following the same rules, the same principles, going from logarithmic form to exponential form. It's just a little bit extra tricky because of the fact that I've got a log on both sides of that equation. So the reason I want to show you this is because this shows the inverse property that we talked about briefly before in a couple of sections before. When you have a base, like here we have a base of 7 raised to an exponent, and that exponent has a base of 7 as well, then all of this stuff cancels out. It's like they undo each other. The logarithm undoes the exponent. And so those go away, and then you end up with 5x equals 2 minus x, which is the same thing we had up here. So I want to show you this because it shows you how the inverse property works and why it works. and how I can go just even on number 31, I could go straight to this first line without having to do all this work down here. All right, number 34 is a little more straightforward. Again, we have log base 4, so I'm gonna take that base of 4, I'm gonna raise it to the 6th, and that's going to equal 3x. So once again, I'm just going from logarithmic form down to this exponential form, just following this pattern here. And then I'll solve from here. 4 to the 6th is going to need to be divided out by 3. And so when you take 4 to the 6th and divide it by 3, you, as long as you follow those order of operations, you should end up with this to the they want you to take it out to 3 decimal places. So it would look like that. On 37, we have a 2 being multiplied by this logarithm. So we need to, just like we had to in the front, get our exponential expression isolated if it were not already. We need to do the same thing with our logarithms. So we're going to divide this out both sides by 2, and that will result in the 2 going away on the left and us having a 6 on the other side. And then from there, we're just going to exponential form. So base of 7 raised to the 6th equals 1 minus 2x. 7 to the 6th power is this right here. And then I'm going to need to subtract that 1 and divide by -2. And all said and done, we should end up with this right here. All right, same thing for number 40 there. The logarithm is not by itself, so we're going to isolate it first by subtracting that 4 from both sides. All right, and then again, so the logarithm is by itself now, the logarithmic expression. The base is not recorded, so we know it's 10. So we're going to say 10 to the first power equals 7x. And now we just solve for x. All right, so that one's pretty straightforward. Some of these are pretty straightforward. 43 is not straightforward. We need to use the product power to raise to combine the left-hand side, those two logarithms. So remember, when we have one of our properties of logarithms says that when we have two logarithms with the same base, that's the important part here. So both logarithms have a base of 6. Because they both have a base of 6 and we're adding them together, then that means we can rewrite it as a multiplication problem. So we can say log base 6, we're just rewriting that because they share that in common. And then we will multiply the 2x minus 6 and that x together, and then keep it set equal to that 2. Okay, we're not ready to move into exponential notation until we have this simplified. This is how condensed. We're condensing these logarithms on the left-hand side. All right, so we just need to finish that multiplication off by distributing the x. That's all I'm doing here is just distributing that x out. And we end up with this right here. And then from here, we can go into our exponential notation. We have everything condensed as far as we can. So I'm going to write the base. That's 6 raised to the second power is going to equal this right here. I probably should have kept that in parentheses to make that a little clearer. All right, and then from here, hopefully you can start to see the beginning of a trinomial, like a quadratic trinomial starting here. So we have our 36 over here. We've got our highest exponent is squared. All right, so that's how we know it's going to be quadratic. If I take the 36 to the other side and solve for 0, then it's going to look just like that right there. All right, so now it's a quadratic equation, trinomial that we can factor. So when we factor, we always look for the GCF first, and fortunately we can pull a 2 out here. And of course we can factor it without doing this. I mean, you know how to factor when the lead coefficient isn't 1, but this is going to make it, so much easier. Pull that out and now you have a lead coefficient of 1. And we can just factor that. Remember, factors of negative 18 that add to negative 3 would be negative 6 and positive 3. Of course, 2 doesn't equal 0, so we're just throwing that constant out. X minus 6 set equal to 0 will give us a solution of 6, and then on this side we'll get a solution of negative 3. So x minus 6 and x plus 3 are our factors. These are our zeros. 6 and negative 3 are the solutions. The directions tell us to check for extraneous solutions, and this is the first one that has had an extraneous solution. And the reason that it does is that the 6 is the answer. The negative 3 is the one that's extraneous. If we take this negative 3 and we plug it back into our original equation, what ends up happening is we get an undefined logarithm. So let me show you that over here on the side. If I take the original equation and plug that negative 3 back in for here, for the x, and that just in that first logarithm, I'll show you what happens. We end up with logarithm base 6 of negative 12 here. And this is an undefined situation. So because if you think about it, what this means is 6 raised to some exponent gives me negative 12. Since there's not an exponent that we can raise 6 to give us negative 12, then this situation right here, when we have a logarithm like this, we say it's undefined. And so since it's undefined, then the solution itself becomes extraneous. So we would throw the negative 3 out and we would keep that 6. You're not always going to be throwing out the negative number, so you can't just assume that. It has to do actually with putting it back into the equation and ending up with a negative in here in the logarithmic form. All right, and then we're going to actually move down to number 50 and do that problem. This is another problem where they've given you a physics equation to use, and it's relating here the velocity, the maximum velocity of a rocket, where they're allowing t to equal the velocity of the exhaust coming out of the rocket. And then m is a ratio, and that ratio is, so that's like a proportion, a numerator over a denominator, where they're going to have the mass of the rocket with the fuel over top of the mass of the rocket without the fuel. And so that's the ratio that is represented by m. And you can see the natural logarithm in this equation as well. So they tell you that you have a solid propellant rocket with an exhaust velocity. So this is your t right here, your exhaust velocity of 2.3 kilometers per second. All right, there's your t. Its maximum velocity is 7.2 kilometers per second. So this is your v. And they want you to find the mass ratio. You're solving for m. And so we're going to plug in the things that we know. 7.2 for our v, 2.3 for our t, and then the natural logarithm of m. M is what we're solving for. So to go, we're in logarithmic form. In order to solve it, we're going to have to go to exponential form, but the first thing we have to do is make sure our logarithm is isolated. So we need to divide through by 2.3. And get this right here when we do that. And now our logarithm is isolated by itself. Right, so I'm going to rewrite the natural logarithm log base e, because we know that the natural logarithm just means log base e. So I'm just going to rewrite it, log base e m. So I'm just taking this and writing it in like that, just so it's a little bit easier to see when we go into exponential form. And then that's going to equal this. I'm just switching sides as well. So this means that when we go into exponential notation, base e raised to that decimal number is going to equal m. So then you'll go into your calculator. You'll raise e to this exponent right here, and that should give you an answer of 22.88. All right, and that's it. So make sure on the word problem you know how to just evaluate those numbers into the correct variable. And then we need to use the skill we learned at the top of the sheet, which is to make sure the logarithmic expression is isolated before we go into exponential notation.